they share a point. And the point on this particular graph, it's easy to see that if I can count my spaces, is 3, 2. This x value for 3, y value for 2 is shared for both of these lines. It's where they both intersect.
Mr. Gonzalez, the screen's
Yes, ma'am.
not quite sharing right. I don't see anything but the welcome screen.
Oh, okay. Let me try again this. Let me stop sharing and then share again. Because on my end, I'm showing that I have the screen, but here, let me exit. Let me stop sharing. Okay. Patricia, do you see it? Do you see this? Do you see the slide?
I see the PowerPoint, but like it's not in presenting view.
I'm sorry?
I see the PowerPoint, but it's not in presenter view.
It's not in presenter.
Current slide, if you click it, what happens?
Let me see. Do you see it now?
No, sir. I just see the background PowerPoint.
Then let me do this. Because I don't know if I'm doing something wrong. Um, let's do this. Then let's just go back. If you want to go ahead and just apply it that way, I can see the chat as well.
Okay.
And then I'll just I'll traverse to it. Let's see how that works. Let's see if the animation works any better with that, or I have a better luck with the screen. Let me go ahead and exit this then.
Oh, okay. So you want me to stop sharing? Reshare?
Yeah, let me go ahead and I'll stop sharing. And then if you want to upload it again through your end. Okay, there we go. And let me see. When I move forward, it just moves everything together. That's fine. I'll just do that.
Okay. I'm sorry.
I think it's just better. No, it's okay. Um, it's okay. Thank you for telling me. Um, and I do have one student, right? Sophia. Sophia's here.
Yes, sir.
Okay. All right. Awesome. So that way I'll direct my questions to her then. All right, Sophia. Let's see here. So, um, let me go back a little bit again, just so, um, or this is our first one. So what I explained to you, I don't know if you got to see it or not, Sophia, is we were testing these points, -1 and 3, to these two lines to see if it was a solution. And when I plugged in these points to these equations, because I got a true statement for both, that is telling me that um, this ordered pair is a solution for these two lines. Okay, so when another thing that I didn't mention. Okay, when we call a system um, of something when we have more than one line. So when we're looking at more than one line or several lines, um, it becomes a system. And for us to solve this system is we want to find out where these lines intersect. We want to know if there's a point that they all share. So that's what we're doing here. Okay, so again, when we tested these points, I saw that -1, 3 was a solution for these two lines. And when I tested 2 and -0.5, 0.5, I saw that it was not a solution. Yes. Um, so I was also mentioning to you that um, one quick way to see if two lines have a solution is by graphing them. And when we graph them, and we see here our example A, we see that this blue line and red line intersect. So we automatically know that this is going to have a solution. And we can on this particular example, we can easily see what that point is because it intersects an exact placement, right? 3, 2. So the only bad thing about trying to solve for linear systems graphically is sometimes the points are not that easy to see, and the best way to get them is algebraically. Okay, um, but um, another thing that you can see that also can help us again to speed up the process. Maybe we want to find out if it has a solution or not before we start doing it algebraically and maybe at the end discover that there's no solution, right? That's why we would like to do it graphically. But if you notice that if you graph two lines and you only have one line, it only produces the two lines produce one line. What that means is there's two ways you can look at it. One is the exact same line, that it's just that they're written differently, but it's the exact same line. Or another way you can think about it is that there's one line on top of the other, meaning it's the same line. So if this happens when you graph two equations and it only produces one graph or one representation, that means that it's the same line. Hence, we have infinite number of solutions. That means that it goes from forever to the left or forever to the right. Um, but it's all of the points in the line. As you know, lines go forever. We do arrows. That means that they go forever. In this case, forever up and forever down, right? Now, if we have no solution, like the example that we had in the beginning, that second one, where we saw that the 2 points was not a true statement for both of the equations, well, when that happens is we have this situation where the two lines are parallel, means that these two lines, I can graph them, but they'll never intersect because they're parallel, okay? And um, when we have this situation where we have no solution or we have parallel lines, we call this an inconsistent system. Okay. When we have a solution, we call this a consistent independent system where we have one answer. And when we have infinite number of solutions, it's still a consistent, but it's a dependent system. Okay. So these are just terminologies to help you understand the material better. Okay. Now, if we look at the graphing method again, if we were to look at these two equations, so the problem would say solve the system by graphing. So we have one equation, y is equal to 3x minus 6, and I like this one because it's in slope-intercept form. It would be easy to graph. So if I would graph the first equation, y is equal to 3x minus 6, I know that it has a y-intercept at -6, and its slope is 3. So I would go up 3, 1, 2, 3, run 1, and those are my 2 points. At 1, -3 would be 1 point, 0, -6 would be my other, and that would be my line here, this purple one. And then the second one, if I wanted to graph it again, um, the best way to do it, either to do a table, but that would take time. So what I would do is I would convert this equation into slope-intercept form, and I would have this, y is equal to -5 half x plus 5. I know that it has a y-intercept at 5. It has a negative slope, so I'm gonna go down 5 and then run 2, okay? And that will be my point. Now there's two benefits of doing this. Whenever they give you two equations that are not in the same format, for instance, the first one was given to me in slope-intercept form, but the second one was given to me in general form. And by me converting it to slope-intercept form, both of them, not only is it going to help me graph, but it could help you some time, because if you noticed on the previous slide, right, we saw that if two lines are parallel, that means that they have no solution. So hopefully you can see that if two lines have the same slope and different y-intercepts, you're going to know that these two lines have no solution. There's no reason for us to graph them, because just by the equations alone are going to tell us that they're going to intersect at some point. Okay. The other thing is that if you put them all in the same format, you could probably find out that it's the same line. It was just written in a different format, and then you'll automatically know that, hey, there's no need for me to graph, because if they have the same slope, same y-intercept, then that means, again, it's the same line, or you can think of that the lines are on top of each other. So hence, I am going to have a dependent system with infinite number of solutions. Okay, so but in this case, again, we had different slopes, we have different y-intercepts, so that means the lines are going to intersect. And to see the solution is where these two lines intersect, right at this point here, which is at 2, 0. Okay, so again, this is the beauty of graphing. And the beauty of graphing makes us see what type of system we're gonna solution we're gonna have, and also helps us to see if it might not have a system. But the only drawback is sometimes that number is not easy to read. What if it was in the middle, right? Like, how do I know if how accurately it is? Is it closer to 0.5, 2.2, 2.3? So that's when we want to really do it algebraically. Okay. Now, so let me introduce to you one way to do it algebraically. If I wanted to solve the system, they're not giving me up to test, but they're actually me to find the solution. Want me to solve if these two lines intersect, what is the answer? So one of the methods is called substitution. And just like the name says, it's really, really, really clear, right? The substitution method means this. Given two equations, you're going to solve for one of the variables. It doesn't matter which one. You can solve for y or you can solve for x. And what you're going to do is you're going to replace it, that variable, into the other equation. Okay. Now, the best way to see this is with the example. Now, in this particular one, they did half the work for us already. They gave us one equation in slope-intercept form, meaning y equals 3x minus 6, and then the other one is in general form. But I said that they made us a favor is because they solve for one of the variables. So I'm going to take that into my advantage. And since they already solved for y, I'm going to replace that y value into the second equation. So I'm going to take the second equation as minus 5x minus 2y equals negative 10. And for the y value in the second equation, I'm going to replace it with 3x minus 6, which is what I did here, right? And that is in the lighter blue. So all I need to do is go ahead and distribute the 2, combine my like terms, and simplify. And when I simplify, I get x equals 2. So believe it or not, this value is shared by both. The fact that I replaced my y value to the second equation, I'm able to see that this 2 is shared by both of these equations. Now, if I want to find the y value, all I need to do is replace it to any of the two equations. Now, let's be kind to ourselves. Since we already solved for y, let's go ahead and plug in that 2 value into that first equation, because once we get our answer, it's going to tell us exactly what y is. So that's what I did here. I replaced the x with a 2 to that first equation, and when I simplify, I end up that y is equal to 0. So this is my solution. Again, this method is called the substitution method. Substitution means solve for one of the variables, replace that variable to the other equation, and you will get your answer, your solution. Okay? All right. Again, Sophia, if you have any questions, please let me know. Please stop me. Okay. So again, um, this is a consistent independent system because I had one answer. Okay. All right. Um, let's look at the elimination method. Okay. Let's skip too many. Here we go. So let's look at the elimination method. Okay. So believe it or not, this method is also clear to see or understandable what we need to do. The elimination method for us is we want to get rid of one of the variables, eliminate one of them. That way we only have one unknown, one variable to solve. So that's what we're going to do now. So to do the elimination method, um, we want to um, get rid of one of the variables. Now, the best thing to do first, since they're both in two different formats, one is in y-intercept form and one is in general form, okay? Maybe you wouldn't see this right away, but what we would want to do is first put them both um, in one format. And in my case, I'm just going to put them both in general form. So the first one I converted into general form by moving my 3x to the other side. Okay, so I have minus 3x plus y equals negative 6. Now that one is in general form. And then the other one I'm going to leave alone. Minus 5x minus 2y minus 10. And what you want to do, in my case, I'm going to get rid of my y's. And in order for me to do that, if my first equation was a 2y and I added it to the second y, 2y minus 2y would become 0. I would eliminate my y's. Okay, but in order for me to do that, I can't just add the 2 to the y. I need to distribute that 2 to the whole equation. That way I don't unbalance the add equation. I want to make sure that I still have the original equation. So when I multiply it to the y, I'm not just going to do it to the y. I'm going to do it to all of the terms in the equation. So the 2 gets multiplied to the negative 3. The 2 gets multiplied to the y. The 2 gets multiplied to the negative 6. So when I do this, I get a negative 6x plus 2y equals negative 12. Now, if I add these two equations together, you'll see that I got rid of my y. And some books, they call this method the addition method, because basically what you're doing is you're adding the two equations together to eliminate one of them. But again, I think in your book, in the intro to 1324, they just call it the elimination method. Okay, so once that I see that I got rid of my y, I'm just left with one variable, the x. I have this equation, negative 11x is equal to negative 22. So to solve for x, I'm going to divide both sides by negative 11, and this gives me the solution x equals 2. Okay, so I have one of the parts of the solution where x equals 2. So now to get the other part, I'm going to do the same thing that I did for my substitution method. I'm going to plug it in to any of the other two equations. And again, I'm just going to plug it into the first equation since it's the easiest one to plug in to get the y value. And when I do this again, I get my solution again, 2, 0. Again, this is a consistent independent system. So again, this method is called the elimination method. Okay. All right. So let's look at this example. Let's see. Am I clicking too fast? Here we go. All right. So let's look at these two examples where we have a demonstration that we're going to have infinite number of solutions, and this is an example where we have a no solution. So if we look at the first example, we have two lines, 3x minus 2y equals 4, and we have 6x minus 4y equals 8. Okay, so I'm going to use the elimination method to see or solve for the solution. So I see that if I want to get rid of my y's again, I need to multiply a negative 2 to the negative 2y, because if I do that, I get a positive 4y, and when I add it to the negative 4y, it will get canceled or eliminated, becomes 0. So that's what I'll do. I'll multiply the negative 2 to the 3, giving me negative 6x. Negative 2 times the negative 2y gives me a positive 4y, and the negative 2 to the 4 gives me the negative 8. And when I add these together, I get this situation. 0 is equal to 0. There's nothing was left over. So what that tells me is that because I added the same line with the same line, everything canceled. It just became 0. So whenever this happens, that you get this statement, 0 is equal to 0, that means it's the same line. It's just one is different than the other. And see, when I multiplied the two, do you see that it's the identical equation? It was just written in a simplified format, or was in a different method, right? Or example. So when you added them, you get to 0. So this means that we have an infinite number of solutions, meaning it's a consistent dependent system. Now, if we look at this number 7 example, right? I have these two equations. Again, I want to solve by the elimination method. I want to get rid of the y, so I'm going to multiply a negative 3 to equation 1. And when I do that, I get a false statement. 0 is not equal to negative 6. So because this is a false statement, what this is telling me that these two equations have no solution, meaning that these two equations never intersect. Hence, it's an inconsistent system. Okay. All right. So let's look at an application problem. So we have this problem. A 200-seat theater charges $8 for adults and $5 for children. If all seats were filled and the total ticket income was $1,435, how many adults and how many children were in the audience? Okay, so we want to solve how many adults bought tickets for us and how many children bought tickets for this theater, right? For this movie, right? So what we need to do in order for us to solve this, we need to solve we can solve by creating a linear system. So let's look at the information that we have. So um, again, as you might expect, in order for us to solve for an x and y value, we need two equations. So we need to extract two equations from this word problem. So the first equation that we can abstract from this word problem is this, that the theater holds 200 seats, okay? And um, that to fill this theater, it would be made out of the adult seats and the children's seats. So um, to get the total of X plus Y um, seats that were sold, this has to be equal to 200 because that's our maximum seating that our stadium can have. Yes? So that's our first equation. Our second equation, we can apply what we know about money, right? To get a, a money or a total or what we owe, right? When we want to buy something, if you want to buy something at the store, to get your total is how many items you're buying times their cost, right? Price times quantity will give me my total. So I know this, that the price of the ticket for the adults is 8. So 8 times X, the unknown number of adult tickets sold, plus $5 the children tickets times Y, which is, I'm saying that the Y is a children's ticket. This should equal our total revenue. And our revenue was $1,435. So 8X plus 5Y should equal 1,435. Voila, now I have my two equations. And these are linear equations. Have X plus Y is equal to 200. 8x plus 5y is equal to 1,435. So for me to solve for the number of adult tickets sold and the number of children sold tickets sold, I'm going to solve. And again, we can use any method. We can use the substitution, we can use the elimination, we can graph them. But for our purposes, let's go ahead and use the elimination method. Yes. So I'm going to eliminate my x value. I'm going to do something different. I'm going to get rid of my x this time. So to get rid of my x, I see that if I multiply a negative 8 to the first equation, and add it to the second equation, that would give me the 0. So that's what I will do. Multiply the negative 8 to the first equation. I get negative 8x minus 8y equals to a negative 1600. When I add it to the second equation, I end up getting negative 3y equals negative 165. As you see, I got it. I eliminated my x value. So now I'm going to solve for my y by dividing by a negative 3 on both sides. So y is equal to 55. So what this tells me is that for me to have gotten this revenue, I needed to have sold 55 of the children's tickets. Now, for me to get the number of adult tickets, well, that's the easy part. I'm just going to substitute it to that first equation and solve for x, the adult tickets. So I'm going to replace that y with the 55 from my first equation, subtract 55 on both sides, and I get x equals 145. So the solution for this word problem or this application problem is I sold 145 of the adult tickets and 55 children tickets. Okay, so as you can see, linear systems and solving for linear systems can be applied to real world applications. It can be very, very powerful to figure out information of this nature, okay, especially in business. All right, so what if we have larger systems? So larger systems means what if we're not just looking at two variables, we're looking at more than two variables, meaning we're looking at basically more than one line or more than one equation. Okay, so um, one way to do this is to do basically an elimination process, okay? And once we do the elimination process, we can work ourselves backwards. So some books call this a backward substitution method, or I think your book just calls it an elimination method. So to solve for larger systems, um, one way, the best way to, or the easiest way, you don't have to do this, but one of the easiest ways to do this is to rearrange the equations where we have the coefficient of one as our first equation. Okay, so and then the others follow suit as far as in size, but just the coefficient of our x value. Okay, but again, you don't have to do this. And what we want to do is we want to eliminate um, variables to where we are down to just one variable. And then once we have one variable, we can work ourselves backwards. So the best way to understand this is just by looking at this example. Okay. So the plan is to get rid of 2 out of the 3 variables. So what I'm going to start is I'm going to take both equation 1 and equation 2, and I'm going to eliminate the x variable from these two equations. And I'm going to do the same thing that I had done before, okay? Except that I'm dealing with 3 variables now. Then that new equation where I eliminated the y variable, I'm going to do it again. I'm going to then now eliminate the y variable, okay? And then add these two equations. And when I do that, I'm going to have a single equation with only the z variable left over. And it's going to give me the value of what that is, okay? So once I have that, I just work myself backwards and replace that one value to to the equation that has 2 variables. And then once I have 2 variables, I'm going to replace it to the equation that has the 3. Okay, so this is what it should look like once we eliminate it to just one variable. So let's go ahead and do a how we got to that point. Okay, so again, let's start off. Again, I'm going to grab equation 1 and equation 2, and I want to eliminate the x variable. So if I want to get rid of the x variable, I see that on my equation 1, there should be a negative 2x there. That way, when I add them together, then minus 2x with a plus 2x gets eliminated or becomes 0. So I'm going to multiply negative 2 to the whole equation. It's very important that we never forget to multiply this negative 2 to both sides of the equation, because that's one of a common pitfall, that we only multiply the negative 2 to the left side and forget to do it to the right side. We want to do it to both sides. So on this one is easy because the right side is 0, right? So we get negative 2x plus 6y minus 4z equals 0. And I'm going to add it to equation 2. And if you notice that when I added it to equation 2, I got rid of my x. So I have 4y minus 3z equals 3. So I'm going to do that again, but I'm going to alter the equations. Now I'm going to use equation 1 and equation 3. Okay, so I'm going to do the same thing. I want to get rid of my x. So, and again, it's my x variable, okay, not my, sorry, joke. I want to multiply negative 3 to the x. So here, when I multiply the x to the negative 3, I get a negative 3x. And if I add it to this positive 3x, it will cancel out, right? So I'll do that to the whole equation, giving me negative 3x plus 9y minus 6z equals 0. I'm going to add it to the second equation. And when I do that, I got rid of my x variable, right? I get 10y minus 7z equals 7. So these are my two new equations that we were talking about earlier. So I'm going to take these two new equations, and now what I want to do is get rid of the y, okay? So what I'm going to do is to get rid of the y. I would do the same thing, right? But let's see here. And I have it here, sorry. So the first equation, to get rid of the y, I'm going to multiply a negative 10 to the 4. So that becomes a negative 40 y. And I'm going to multiply a 4 times a 10 to get a positive 40y. So if you notice, before we had only had to multiply one one of the equations for it to be the opposite sign and but equal value to the other. On this particular one, since they were, I can't make a 4 into a 10 and I can't make the 10 into the 4. I had to find the least common multiple. Okay, and I want the least because I don't want to work with large numbers. So what I see is that the least common multiple between 4 and 10 would be the 40. So that's why I did this. This is why I multiplied a negative 10 to the 4 and the 4 to the 10. Okay, and I wanted them to have different signs. That way when I add them together, they cancel. So when I do this and I add these two equations together, do you see that I got rid of my y's and I ended up with 2z is equal to negative 2. So if I divide both sides by 2, I see that z is equal to negative 1. So now I have the example that I had just given to you before. Um, I have one equation that has just one unknown, and then I have two equations, the second equation that has just two unknowns. Sorry, give me 1 second, okay? All right, Sophia, sorry about that. Okay, um, so I have this situation. So if I want to solve, I already have one of the variables that is part of my solution. Z equals negative 1. So now I'm going to work backwards. I'm going to plug in this Z value that I know negative 1 to the second equation where it has just the Y and the Z. And when I do that, I get that where am I? Where am I? Where am I? I have here Y equals 0. Okay. So now I have two variables of the solution. To get the last one, to get the x, I'm going to plug in the negative 1 and the 0 to the first equation that has the three unknowns, and it's over here, right? So we have um, x minus 3 times 0 plus 2 times the negative 1 is equal to 0, and when I solve, I get x equals 2. So the solution for this larger system is x is 2, y is 0, and z was negative 1. Okay, so it's basically the same process, even if we have a larger system. Um, we just apply the same concept. Now, there's another way to solve for larger systems, and that's by using matrices. Okay, so and matrices are awesome to solve, and it's the same process. It's the same process that I use to solve the larger systems. We can do it with matrices, but one of the other benefits that if to use matrices that maybe your instructor will show you that how you can use your calculator to solve these, okay, and it make your life a lot easier. But for right now, I'm going to show you how to solve them by hand, okay, solving them with paper. So our objective is to convert our linear system into a matrix, and that name of that matrix is called an augmented matrix, okay? So some instructors might test you on just converting a linear system to its augmented matrix form, okay? And then once we have it in its augmented matrix form, we need to solve it by having this row reduction elimination method. And then I'll explain a little bit of what that means. And like and Mr. Isasi has this, like how can I get from this to this, right? How can I get from this to have the solution x equals 2, 0, y equals 0, and z equals negative 1. Okay, so first let me see if he has it. If not, no, let me talk about this first. Just very quick. How do I convert a linear system into an on-matrix matrix form? Um, all you need to do is make sure you grab only the coefficients of the equation. So if you see here, our system has three variables, the x, y, and z. So I'm going to have three columns that include the x, the y's, and the z. Okay. The equal in matrices is represented by this vertical line. Okay. This vertical line means equal in matrix. Okay. So to the right of our equal signs, we have the 0, 3, 7, and that's where I'm going to plug in these 0, 3, 7. So again, I'm only going to grab the coefficients. So here I had a 1, -3, 2 as my coefficients for the x, y, and z equals 0. For the second equation or second line, we have 2, -2, 1 equals 3, just the coefficients. And then for the last equation, we have 3, 1, -1 equals 7. Okay. Now, let me show you, okay? And I'm gonna skim through this sort of quickly. Again, keep in mind that you are welcome to download this presentation just by clicking that little box with the arrow on your screen. You can download the presentation so you can review it later. And the reason why I'm telling you this is because I want to skip through this because what Mr. Isasi did, he did like this awesome color coding step-by-step procedure on how to get from here to here. But I think the best way to also understand it since I'm here is just to do it through the example, okay? So again, I'm going to skip through these slides because it shows you how to get from one point to the next point. But let me go ahead and show you how this is done physically, okay, with this example. So what you're going to do is a series um, of steps that involve the rows, okay? And it's basically you're doing elimination method, but in a condensed method, okay? So if you see here, if I look at my answer, right? I want it to be 1 0 0 0 1 0 0 0 1. And the best way to also understand what's happening here on the left side, think of your intercepts, right? If I wanted to solve for the x-intercept, I set y equal to 0, right? In my equation, I have a y and a z. So if I just want to know what the x value is, I want the y value and the z value to be 0. And if I do that, I have my x-intercept, what the x value is. In this case, is 2. If I want to find my y value, it's like finding my y-intercept. To find my y-intercept, I set x equal to 0, z equal to 0, and that's going to give me my y value answer. It's the same with my z value, right? So um, I have, if I want to find my z intercept, I would set x equal to 0 and y equal to 0, okay? So this is what's happening here. So we want this. So we're going to do elimination method to do that. Okay, so we already have a 1 here on the row 1, so that we're going to leave it alone. So whenever we don't have to touch a row, we just leave it alone. But we want a new row 2 and we want a new row 3. We want row 2 on this first column to be 0, and on row 3 we want this also to be 0. Right now we have a 2 and a 3. Now, the first thing that I also want to mention to you, again, Mr. Isasi did a great job to show you the steps on how to do this. This procedure is a step process. You don't want to break from these steps, because if you do, you'll end up going in circles and you'll undo something that you've done in the past. So the best way to see how we're using matrices to solve is think about it this way. Just the way you read a book, right? You read a book from left to right, or when you're reading graphs, right? In math, you've been dealing with graphs and you read graphs from left to right. Well, that's how you're going to solve these matrices as well. We're going to always work from left to right, and we're going to go column by column. So do you see here we have 3 rows, and then we have also 4 columns. Okay, so when we're solving these, we're going to go through column 1, column 2, and column 3 in this order. Okay, and we don't want to deviate from that. Okay, all right, so let me show you the syntax. So here I want to eliminate the 2 and the 3 from these examples. So here the 2, the least common multiple between 2 and 3, okay, for this one would be like 6, right? So I would want to multiply a 3 to row 2 to make that a 6. And then I would need to multiply a 2 to row 3 to make that a 6. But again, Mr. Isasi has it as negative for either one. That's you can decide which one you want the negative. Okay, so um, in order for them to eliminate, one of them has to be negative. Yes? So once I do that, once I multiply a negative 2 to row um oh, and actually he's using the row 1. Sorry. I My apologies. Again, I can use row 2 and row 3 to eliminate, but what Mr. Sassi did on his example, he uses row 1 to eliminate them. Okay, so he's getting the least common multiple between 1 and 2, and he's getting the least common multiple between 1 and 3. Okay, so I do apologize. He's using row 1 to eliminate. So that's not a problem. But again, hopefully you see that's the same concept. Okay, so I'm going to multiply negative 2 to row 1 to get a negative 2 here. So when I add it to row 2, it eliminates that 2. And I'm going to multiply negative 3 to row 1 in order to, when I add it to row 3, it gets eliminated. And he did a little scratch work here. So he did what I just talked about here. And again, you need to know this, okay? You might be tested on the syntax on how you're getting your augmented matrix solved. You need to know this syntax, okay? So this that we just wrote, we did a little scratch work. We multiplied a negative 2 to row 1. That gives me this. I'm just going to add it to row 2. He's not doing anything to row 2. And when I add this, look what happens. The negative 2 plus 2 gets 0. That's what goes there. The 6 minus 2 is 4. That goes there. The minus 4 plus 1 minus 3 goes there. And the 0 plus 3 goes there. And then I do the same thing. This syntax here, the negative 3 row 1 plus row 3 is down here. It's the scratch work here. I'm multiplying a negative 3 to row 1. That gives me negative 3, 9, negative 6, 0. And then I add it to row 2, to row 3, and I get 0, 10, negative 7, and 7. So it's right here. So this is the process. I'm going to go and traverse to what Mr. Isasi gave you the steps. Again, we want to always have this situation where we have 1 0 0 0 1 0 0 0 1. So I got this first column. So now I move to the second column. Okay. So if you see what he did here is row 2 doesn't get altered. It has a 4 there. I'll take care of that 4 later. But what I want in this new second column, I want a 0 here where that negative 3 is, and I want a 0 here where that 10 is. So again, he writes the syntax here to get rid of those. This is his scratch work, and when you simplify, you get these values. 4, 0, negative 1, 9, 0, 0, 1, negative 1. Okay? And then I move on. I go on to the last column. Now that I have a 0 here, I want to have a 0 here where the one's in red. Again, I love what he did. He color coded everything so you can see what he's doing. Okay, so again, we want to eliminate these two. So what he does is he uses the one that doesn't get altered to get rid of those. So he uses row 3 to alter the others. Okay, and that's a good thing to do. Okay, it's a smart way to do. Use the one that you're not changing to get rid of the other variables. Okay, so always do that. The one that you're not touching or not changing anything to it, use that one to eliminate your variables. Okay, so again, we're getting rid of this negative 1, 3, so he multiplies it 3 to row 3, added to row 1. He multiplies it 3 to row 3 to add it to row 2, and we get this 0, 0, 1, 2, 0, negative 1. So see, we have our solution. We have now solved for it by having technically the intercepts. I have a 1 for the x, 0 for the y, 0 for the z, 0 for the x, 1 for the y, 0 for the z. We have 0 for the x, 0 for the y, 1 for the z. And the right side, what this is equal to, this is telling me that x is equal to 2, y is equal to 0, and z is equal to negative 1. Okay? So again, I have 5 more minutes. Let me see. He has just the steps that he's comparing the steps that we did all together on one slide. Again, it probably might look nicer when you download it. He has an animation for this. That's why for me it's a little bit hard to follow because the animation would be the one that would be leading the step-by-step process. Okay, so I guess in the last 4 minutes, what I want to do is just let me um, quickly just run through this application problem, like this real world problem. And you can see that we can use matrices to solve this as well. So we have another venue instead of a movie. Now it's a concert, right? Where we have three types of tickets sold: adults, teenagers, and preteens. You know, kids, children, right? So now we have three unknowns or three different types of tickets. And there are 570 people in the concert. Oh, that's the same process that we had before. If we say that X equals the adults tickets, Y the teenagers tickets, and Z the preteens or the children, that should equal to the number of total people attended. So in this case is 570. So our first equation is X plus Y plus Z is equal to 570. And then we can use what we know of revenue to calculate our second equation, right? Price times quantity will give us our revenue. So here we can see that 5 times X plus 3 times Y times 2 times Z, the price of each ticket, times the number of either adults, teenagers, or preteens that attended should equal our revenue, which is 1,950. Okay, so now on this one, we would do the same thing. We want to get rid of our equations, okay? Get rid of two unknowns, get rid of, then once we have getting rid of, sorry, one unknown, then we have two unknowns, then we have two unknowns, we get rid of another unknown, and we're able to solve it. So again, he puts it on here for you to try it, right? Try to solve this by doing our backward substitution or eliminating to just one variable, so you can get your answer of we sold 220 adult tickets, 150 teenager tickets, and 200 preteen tickets. Okay, so again, I hope I didn't go too fast. Um, if you have any questions for me, please let me know. If not, thank you for attending. I'm sure Mr. Isasi will come back our next time we meet. Okay?
Okay, thank you, Mr. Carrizales, for presenting today. And let me just give them a few announcements before we go.
Thank you, sir.
So the next 2 weeks, we're gonna be off for Cesar Chavez Day and Good Friday, and then we will be back on April 14 for review for exam 3. And thank you again for coming, and we hope to see you again.